Hello. Today we will speak about another property of known space, what's called completeness. So our paragraph will be called complete normal spaces. Let X is normal space, and let us have a sequence in this space, and this sequence is called fundamental. If norm between xn and xm goes to 0 when n and m go to infinity. Strictly speaking, it means what for each epsilon we can find a number and such what xn minus xm smaller than epsilon for each n and m bigger than n. It can be easily proved what if our sequence is convergent, then it is fundamental. We just need to use the triangle inequality and recall what if sequence is converged to x, then this distance goes to 0. So each convergent sequence is fundamental, but opposite happens only in complete spaces. So the definition X is called complete normal space, or another name, Banach space. In honor of Polish mathematician Stefan Banach, who invented it. If for each fundamental sequence we can find limit. So each fundamental sequence converges to some element of the space. Completeness is a property of all normed space. So in some spaces this property takes place, in others it doesn't. So we will consider several examples. First example, simplest space of real numbers, and norm is equal to absolute value of this number. For real numbers there is a so-called Cauchy theorem. What says, in our terms, it says what this space is complete. I will not prove it, it should take at least a lecture, and hope you did it in mathematical analysis. So, if xm minus xm converge to 0 and n and m converge to infinity, then we can find element in R such what xm converge to this element. Using our notation, it exactly means what space R is complete. Next example is about space RD, d-dimensional vectors. For example, let us take a norm which is calculated like this. We take some p and in this interval, and then calculate the norm. And we can prove what this space is also complete, so Banach space. In order to do it, let's consider this difference. Let's consider what it goes to 0 when n and m go to infinity. If this root of the order p goes to 0, then the sum itself also goes to 0. we have sum of non-negative components, so it can converge to zero only if each component converges to zero. So So for each coordinate we have this relation. Let us take once again the root of order P from this, and we obtain what x n k minus x n k go to 0 and n go to infinity. For each k. So the fact what our sequence is fundamental implies fundamentality of numerical sequence of each coordinate, of first, second, and so on. So each coordinate of this vector form fundamental sequence, but it's numerical sequence, and as we know, space of numbers R is complete. So there is a x k of R say for each k from 1 to d. We can find the elements such what x and k converge to xk with n go to infinity. So component wise our sequence converges to x, means what sequence of vector converges to x in Rd. As we remember, the convergence in Rd is component wise. Okay. Next example. Let's consider space of continuous function with norm defined like this. We already proved what it is norm space. Let's prove what it is also complete. Let's consider fundamental sequence. It means what supremum converge to 0 with n and m converging to infinity. So it also takes place for each argument x. Once again, if we fix x, we deal with numerical sequence of real number. So we can find a number such what so we have find the function, what is the candidate to the role of limit of this sequence. It is not, we did not yet prove what it is indeed the limit, because here we have, say, component-wise convergence, and as we remember, convergence in this space C is uniform, so it's different form of convergence, and also we have to prove what this function is continuous. Let's try to do it. Let's write it once again in terms of epsilon. For each epsilon we can find the number n such what fn minus x supremum for x is fn x minus x is smaller than, let's say, half epsilon. For each n and m, we will equal with when is n. It means what this estimation take place for each element in this segment. So for each n and m, and for each x from this segment, we have this estimation, this inequality. And let's do following thing. We fix n and let m go to infinity. In this inequality, we send m to infinity. We know what fm at x from x converge to f from x, and so fn from x minus fn f from x converge, n is fixed, m goes to infinity, so it converges to fn from x minus f from x. If we have inequality for each element of sequence, the same but not strict inequality is fulfilled for a limit. So we can say that for each epsilon we can find an n such what fn from x minus f from x smaller or equal than half epsilon for each x and for each n bigger or equal than n capital. If we have inequality what is fulfilled for all x's from the segment, the same inequality is fulfilled for supranon. So supranon over all x's of this difference estimated by half epsilon for each n, what is smaller than epsilon, for each n bigger or equal than n capital. It means what fn converges to f uniformly in AB. And last, we need to recall a theorem from mathematical analysis what says what uniform limit of continuous functions, sequence of continuous functions, is also a continuous function. So this theorem says us what f also is continuous function. And so fn converges to f in our space. So we have proved what this space is complete, so it is one space. Next example we will do in exercises. Space of sequences LP is also one space, and also space L infinity is space of bounded sequences. Here we will consider one more example, also partly here, partly in exercises, but all previous examples are examples of complete spaces. Let's show what we can find also an incomplete space. Once again, let's consider continuous function. Let's denote denoted as C with integral on the segment. Elements of this space are continuous functions. On this segment, and the norm is defined by the integral. So norm is an integral of absolute value of function. Let's prove what it is not complete. How can we prove it? We can show an example of fundamental sequence what doesn't have a limit. Let us consider this example. It is easy to put to consider concrete segment minus 1, 1. And let us define piecewise linear functions with such form. Our function fn is constant minus 1, sorry, on this lower segment. I will draw by blue, minus 1, and it is equal to 1 on this segment, and between minus n and n and minus 1nth and 1nth it is linear. So this is our function fn. So analytically it can be written like this: fn from x is equal to minus 1 if x is smaller or equal than let's say belongs to minus 1 minus 1 and x belongs to minus 1 and 1 if x belongs to 1 So constant, then rapidly grows, then constant once again. For another index m, for example, it will be another function. Let me draw it by green. Something like this. It is fm. Well, obviously m in my example is bigger than n. Please prove what if we define this sequence like this, it is indeed fundamental. And let's consider why it is not converging. Let us assume what Fn converges to F in our space C with integral. F is some continuous function, so convergence in this case means what integral of different converge to zero and converge to infinity. Both functions are continuous. If integral on all interval converge to zero, if we consider a smaller interval, I use red marker for it, from -1 to -epsilon. -1, -epsilon. If integral on big segment converge to zero, then integral for smallest segment is also converge to zero. So from -1 to -epsilon, it is also converge to zero. But let's see how our functions behave on this segment. Here is an epsilon, and if n is big enough, our function fn is constant everywhere on this segment, so it begins to grow only after the border of this segment. So starting from some number, both these values of this function doesn't depend on epsilon anymore. So if actually n is 1n is smaller than epsilon, so this integral doesn't depend on epsilon anymore. And what value converge to zero and doesn't depend from n simultaneously. So xn converge to tn converge to zero, and tn doesn't depend on n. Only one value can do it, 0. So the functions in this bracket need to be equal to 0. So it means what here on this segment it is -1, so it is also need to be -1. So f of x is equal to -1 for each x from this segment. Similarly, it can be proved what our limit needs to be equal to 1 for each x from 1 to from epsilon to 1, sorry. So here, if we consider this segment and repeat this arguing. Okay, so our limit function is continuous, and it obtains -1 here and 1 here. But there is a theorem from mathematical analysis. What if function is continuous on closed segment -1, 1, it is uniformly continuous, and it cannot change much for big value on very small interval. So if interval is small, the change of variation of function is also need to be small. But here on infinitely small interval between -epsilon and epsilon, the function changes from -1 to 1 to very big drop. So it's impossible for continuous functions, and so our limit cannot be disobeys the property of continuous function. So we have no limit in of this sequence, so our space is not complete. In exercises we will study it a little bit more deep, proving what this sequence is fundamental, and but for lecture part is over. Thank you.